Tantor Audio, a division of Recorded Books, presents The Prime Number Conspiracy, The Biggest Ideas in Math from Quanta. Edited by Thomas Lin. Forward by James Glick. Narrated by Bob Souer. Men fear thought as they fear nothing else on earth, more than ruin, more even than death. Thought is subversive and revolutionary, destructive and terrible. Thought is merciless to privilege, established institutions, and comfortable habits. Thought is anarchic and lawless, indifferent to authority, careless of the well-tried wisdom of the ages. Thought looks into the pit of hell and is not afraid. It sees man a feeble speck surrounded by unfathomable depths of silence, yet it bears itself proudly, as unmoved as if it were Lord of the universe. Thought is great and swift and free, the light of the world and the chief glory of man. Bertrand Russell, Why Men Fight. Forward. James Glick. It is sometimes said that writing about music is like dancing about architecture, a category mistake. If so, where does that leave writing about mathematics? The writer has only words, and the mathematician inhabits a different place entirely. Like music, mathematics draws on deep wells of creativity and inspiration, and it can be dark down there. Even the best mathematicians have trouble explaining their own uncanny mental lives. This creates a challenge for the poor journalist. Long ago, I asked Benoit Mandelbrot, the founder of fractal geometry, to describe the source of his intuition about these fantastic shapes and the peculiar methods he had invented. By intuition, mathematicians don't mean clairvoyance, but rather a sense of what is correct. He explained it as merely an exercise of the will. Intuition is not something that is given. I've trained my intuition to accept as obvious shapes which were initially rejected as absurd, and I find everyone else can do the same. In one of the fine profiles and interviews you'll hear in this book, Siobhan Roberts presses the great Michael Atiyah, now 89 years old, to describe how inspiration arrives, and he at least tries. The idea floats in from heaven knows where. It floats around in the sky. You look at it and admire its colors. It's just there. And then at some stage, when you try to freeze it, put it into a solid frame, or make it face reality, then it vanishes. It's gone. Why should they have to explain anyway? Let mere mortals do that for them. As you will hear repeatedly in this book, inspiration strikes willy-nilly. Peter Sheba was at a bus stop in Cuernavaca, Mexico, watching drivers pay cash for slips of paper that recorded the departure times of the buses ahead. It made him think of quantum chaotic systems. Yitang Zhang was in a friend's backyard in Colorado, waiting to leave for a concert, when the solution suddenly came to him, a way forward to proving a landmark theorem of number theory. A retired German statistician was brushing his teeth when he saw the key to solving the decades-old Gaussian correlation inequality. Natalie Wolchover describes this moment as Thomas Royan's bathroom sink epiphany. Like so many others, Royan struggles to find words to express the ineffable joy that comes with this kind of discovery. It is like a kind of grace, he told Wolchover. We can work for a long time on a problem, and suddenly an angel, which stands here poetically for the mysteries of our neurons, brings a good idea. They are just a few of the pioneers we meet here. Marina Vyasovska, a Ukrainian now in Switzerland, packs spheres in 8 dimensions, while Mikhail Rao in France tiles the plane. Martin Heirer remembers exploring the Mandelbrot set when he was a 13-year-old with a Macintosh II. Miriam Mirzakhani wins the Fields Medal for making connections between the geometry of hyperbolic surfaces and physics of dynamical systems. And Artur Avila, another Fields medalist, solves, spoiler alert, the 10 Martini problem. Of the arts and sciences, mathematics is among the most ancient and, at the same time, the most modernistic. It can be beautiful and it can be arcane, and its practitioners treasure both qualities. People who write about mathematics and mathematicians learn to embrace these contradictions. In my own early days exploring the subject as a journalist with no mathematical training, I resented the notion that I was, or should be, a popularizer. The best writing on mathematics does not aim merely to translate or explain. It brings news, bulletins from the frontiers of thought, and it provides us with new ways of seeing the world around us, even the parts that are invisible. What do you do when you get to the gnarly bits, the intricacies that seem just too difficult to grasp? Whether you're a listener or a reporter, I think the answer's the same. Plunge ahead. It is necessary to contemplate the nature of infinity. All right then. On the one hand, there is not just one infinity, there are many. On the other hand, infinity may not exist. It may not be part of reality. It may be a creature of our limitless imagination. If along the way we need to wrap our minds around Ramsey's theorem for pairs or RT22, so be it. I treasure something David Foster Wallace once wrote. It is at the higher and apical levels of geometry, topology, analysis, number theory, and mathematical logic that the fun and profundity start, when the calculators and contextless formulae fall away, and all that's left are pencil and paper and what gets called genius, that is to say, the particular blend of reason and ecstatic creativity that characterizes what is best about the human mind. While I'm quoting Wallace, here is an apt footnote he attached to a review in the journal Science. He worries that anyone writing about mathematics must bear in mind the wide variability in readers' prior knowledge. He quotes G.H. Hardy's famous 1940 essay, A Mathematician's Apology. On the one hand, my examples must be very simple and intelligible to a reader who has no specialized mathematical knowledge, and on the other hand, my examples should be drawn from puka mathematics, the mathematics of the working professional mathematician. Even writing for Science, Wallace realizes that he doesn't know whether he needs to spell out the definition of the Goldbach conjecture, that every even integer greater than 2 can be expressed as the sum of two prime numbers. As it happens, Wallace's footnote concludes, this reviewer is not certain whether it's necessary or not, and the fact that these lines have not been deleted by Science's editors, that is, that you are reading them at all, may indicate that the editors are not totally sure either. Writing about mathematics can get very meta. Some of the greatest problems are also some of the oldest. The highest peaks of mathematics remain in sight of what we learned as children. Several of the breakthroughs reported in this book involve prime numbers. You know what prime numbers are, but it's customary to explain. Numbers divisible only by 1 and themselves, or some such. Many proofs concerning prime numbers fill the annals of history, one being that there are infinitely many of them. This was proved by Euclid, whose dates of birth and death have been lost in the mists of time, who lacked internet access and electricity and, for that matter, books, who had only papyrus to write on and scarcely anyone to appreciate his discoveries. Euclid did not know that he lived on a planet orbiting the sun, but he knew that prime numbers continue to infinity, and he proved it. Where proofs have not yet been found, we have conjectures, such as Goldbach's, that may someday grow up to be proofs. If you can talk about primes, you can talk about the gaps between primes. Often the gap is just 2, as with 11 and 13. They are twin primes. How many of these pairs are there? No one knows, but the twin primes conjecture says they are infinite. By the way, if mathematicians were physicists, they would say these conjectures are true. The weight of evidence is enormous. All their experience says so. Mathematicians peer deeper and deeper into their universe, computers serving as their telescopes and spaceships. As they calculate larger and larger numbers, both the Goldbach and the twin primes conjectures continue to hold up. But that's not good enough for a mathematician. A proof is needed to provide certainty, and in some sense a proof is needed to explain why. In reporting on new progress in the understanding of primes and prime pairs, Erika Klareich tells us about sieves, a method of finding primes by filtering out the non-primes. Sieves go back to Eratosthenes, but the algorithms are improving. Sieves lead to combs, which have teeth. All these words have powerful new meanings assigned by specialists: groups, motives, weights, graphs, matroids, donuts. One well-known feature of prime numbers is that there is a fundamental randomness in their distribution. That randomness is punctured, however, by surprising patterns. The interweaving of randomness and regularity, underlying structure amid disorder, is a running theme in this book, as indeed it is throughout modern science. A mathematician, like a painter or a poet, is a maker of patterns, Hardy wrote in his Apology. His insistence on the apparently unscientific quality of beauty as a touchstone reflects an appreciation of that mixture of order and disorder, because we humans perceive neither pure randomness nor perfect regularity as beautiful. We appreciate a bit of chaos. Perhaps there was a time when mathematics was pure and the lesser sciences coped with real-world messiness. But if so, that time is gone. Mathematicians often lead the way in seeing connections between seemingly unrelated physical systems. As Kevin Hartnett reports, the geometry of random walks may apply as well to quantum strings as it does to bacterial colonies. Mathematicians studying periods of motives are drawing links between algebraic geometry and the Feynman diagrams favored by particle physicists. This is what the physicist Eugene Wigner used to call the unreasonable effectiveness of mathematics. Mathematicians burrow into their world of Platonic imagination, and what they find there, rules, structures, and patterns, reappear in the natural sciences as if by coincidence. In his essay, Robert Deichroff quotes two great scientists 4 centuries apart, each of whom expressed the relationship between mathematics and the rest of science in terms of learning a language. First, Galileo. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics. And then Richard Feynman. To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty, of nature. If you want to learn about nature, to appreciate nature, it is necessary to understand the language that she speaks in. A new language, Deichroff suggests, comes to us from the bizarre world of quantum theory, where things can seem to be in 2 places at the same time and are subject to the laws of probability. He proposes that mathematicians can learn from the unreasonable effectiveness of quantum theory. Indeed, mathematics and quantum theory are cross-pollinating in unexpected ways. The mathematician Svitlana Maiboroda is using the landscape function to perform quantum simulations of how electrons are localized in disordered materials, a breakthrough that may boost the efficiency of LEDs. Other mathematicians are looking at the evolution of quantum states in quasicrystals. The advantage of the quantum language, as Deichroff sees it, is that its holistic approach considers all the possibilities of a system as one ensemble. This holistic approach of considering everything at once is very much in the spirit of modern mathematics, he tells us, where the study of categories of objects focuses much more on the mutual relations than on any specific individual example. Like physicists, when mathematicians discover facts about their universe, they want to connect them to other facts. They want nature to make sense. Introduction. Thomas Lin, Quanta Magazine Editor-in-Chief. It's hard to beat a good science or math story. Take the events of July 4, 2012. That morning, scientists at the world's biggest physics experiment, the Large Hadron Collider near Geneva, Switzerland, made the biggest announcement of their lives. After investing 20 years in the effort to design and construct the LHC, only to suffer a demoralizing malfunction soon after it went online in 2008, they had finally discovered the Higgs boson, a particle without which life and the universe as we know it could not exist. The next year, Peter W. Higgs and François Englert, whose theoretical work in the 1960s predicted the Higgs particle, won the Nobel Prize in Physics. The documentary film Particle Fever chronicled the hopes and dreams of the thousands of researchers behind the Higgs discovery. In one of my favorite scenes, the theorist David Kaplan is shown in 2008 explaining to a packed lecture hall why they built what the experimentalist Monica Dunford calls a 5-story Swiss watch. Unmoved by Kaplan's talk, an economist demands to know what people stand to gain from the multi-billion-dollar experiment. What's the economic return? How do you justify all this? I have no idea, Kaplan answers bluntly. He must get this question all the time. Patiently, he explains that big breakthroughs in basic science occur at a level where you're not asking what is the economic gain, you're asking what do we not know and where can we make progress. In their purest forms, science and mathematics are not about engineering practical applications or cashing in on them, though those things often do happen later, sometimes much later. They're about learning something you didn't know before. So what is the LHC good for? Kaplan asks the economist, setting up the death blow. It could be nothing other than just understanding everything. As it happens, this book picks up where Particle Fever leaves off in telling the story of the quest to understand everything. The renowned theoretical physicist Nima Arkani Hamed has described such efforts in fundamental physics as trying to understand, in the simplest possible way, the smallest set of basic principles from which everything else in principle follows. The fewer the assumptions, the approximations, the contortions, or so the thinking goes, the closer we are to the truth. The Higgs boson has been discovered, and the standard model of particle physics is now complete. The problem is, absent new particles beyond the standard model, the universe doesn't make sense. How, then, are we to make sense of it? In Alice and Bob Meet the Wall of Fire, the biggest ideas in science from Quanta, and The Prime Number Conspiracy, the biggest ideas in math from Quanta, we join some of the greatest scientific and mathematical minds as they test the limits of human knowledge. The stories presented in these two companion volumes reveal efforts over the past 5 years or so to untangle the mysteries of the universe, its origins and basic laws, its contents big and small, its profoundly complex living inhabitants, and to unlock the universal language of nature. They penetrate the big questions and uncover some of the best ideas and theories for understanding our physical, biotic, and logical worlds. Meanwhile, they illuminate the essential issues under debate as well as the obstacles hindering further progress. In selecting and editing Quanta Magazine articles for these volumes, I tried to venture beyond the usual mixtape format of best-of anthologies and greatest hits compilations. Instead, I wanted to send listeners on breathtaking intellectual journeys to the leading edge of discovery strapped to the narrative rocket of humanity's never-ending pursuit of knowledge. But what might those excursions actually look like? These non-fiction adventures, it turns out, explore core questions about the essence of prime numbers, whether our universe is natural, the natures of time and infinity, our strange quantum reality, whether space-time is fundamental or emergent, the insides and outsides of black holes, the origin and evolution of life, what makes us human, the hopes for and limitations of computing, the role of mathematics in science and society, and just where these questions are taking us. The stories in these books reveal how cutting-edge research is done, how the productive tension between theory, experiment, and mathematical intuition, through triumphs, failures, and null results, cuts a path forward. What is quanta? Albert Einstein called photons quanta of light. Quanta Magazine strives to illuminate the dark recesses in science and mathematics where some of the most provocative and fundamental ideas are cultivated out of public view. Not that anyone is trying to hide them. The work hides in plain sight at highly technical conferences and workshops, on the preprint site archive.org, spelled arxiv.org, and in impenetrable academic journals. These are not easy subjects to understand, even for experts in adjacent fields, so it's not surprising that only Higgs-level discoveries are widely covered by the popular press. The story of Quanta began in 2012, just weeks after the Higgs announcement. With the news industry still reeling from the 2008 financial crisis and secular declines in print advertising, I had the not-so-brilliant idea to start a science magazine. The magazine I envisioned would apply the best editorial standards of publications like the New York Times and the New Yorker, but its coverage would differ radically from that of existing news outlets. For one thing, it wouldn't report on anything you might actually find useful. This magazine would not publish health or medical news or breathless coverage of the latest technological breakthroughs. There would be no advice on which foods or vitamins to consume or avoid, which exercises to wedge into your day, which gadgets are must-buys. No stories about crumbling infrastructure or awesome feats of engineering. It wouldn't even keep you updated about the latest NASA mission, exoplanet find, or SpaceX rocket launch. There's nothing wrong with any of this, of course. When accurately reported, deftly written, and carefully fact-checked, it's news you can use. But I had other ideas. I wanted a science magazine that helps us achieve escape velocity beyond our own small worlds, but is otherwise useless in the way the LHC is useless. This useless magazine became Quanta. My colleagues and I also treat our readers differently. We don't protect them from the central concepts or from the process of how new ideas come to be. Indeed, the ridiculously difficult science and math problems and the manner in which an individual or collaboration makes progress serve as the very conflicts and resolutions that drive Quanta narratives. We avoid jargon, but we don't protect readers from the science itself. We trust readers, whether they have a science background or not, to be intellectually curious enough to want to know more, so we give you more. Like the magazine, this book is for anyone who wants to understand how nature works, what the universe is made of, and how life got its start and evolved into its myriad forms. It's for curiosity seekers who want a front-row seat for breakthroughs to the biggest mathematical puzzles and whose idea of fun is to witness the expansion of our mathematical universe. If I may offer an adaptation of Shel Silverstein's famous lyric invitation, my sincere apologies to the late Mr. Silverstein. If you are a dreamer, come in. If you are a dreamer, a thinker, a curiosity seeker, a theorizer, an experimenter, a mathematikaire, if you're a tinkerer, come fill my beaker, for we have some mind-bendin' puzzles to examine. Come in, come in. 1. What's so special about prime numbers? Unheralded mathematician bridges the prime gap. Erika Klarreich. On April 17, 2013, a paper arrived in the inbox of Annals of Mathematics, one of the discipline's preeminent journals. Written by a mathematician virtually unknown to the experts in his field, a 50-something lecturer at the University of New Hampshire named Yitang Zhang, the paper claimed to have taken a huge step forward in understanding one of mathematics' oldest problems, the twin primes conjecture. Editors of prominent mathematics journals are used to fielding grandiose claims from obscure authors, but this paper was different. Written with crystalline clarity and a total command of the topic's current state of the art, it was evidently a serious piece of work, and the Annals editors decided to put it on the fast track. Just 3 weeks later, a blink of an eye compared to the usual pace of mathematics journals, Zhang received the referee report on his paper. The main results are of the first rank, one of the referees wrote. The author had proved a landmark theorem in the distribution of prime numbers. Rumors swept through the mathematics community that a great advance had been made by a researcher no one seemed to know, someone whose talents had been so overlooked after he earned his doctorate in 1991 that he had found it difficult to get an academic job, working for several years as an accountant and even in a Subway sandwich shop. Basically, no one knows him, said Andrew Granville, a number theorist at the University of Montreal. Now suddenly he has proved one of the great results in the history of number theory. Mathematicians at Harvard University hastily arranged for Zhang to present his work to a packed audience there on May 13th that year. As details of his work emerged, it became clear that Zhang achieved his result not via a radically new approach to the problem, but by applying existing methods with great perseverance. The grand experts in the field had already tried to make this approach work, Granville said. He's not a known expert, but he succeeded where all the experts had failed. The problem of pairs. Prime numbers, those that have no factors other than 1 and themselves, are the atoms of arithmetic and have fascinated mathematicians since the time of Euclid, who proved more than 2,000 years ago that there are infinitely many of them. Because prime numbers are fundamentally connected with multiplication, understanding their additive properties can be tricky. Some of the oldest unsolved problems in mathematics concern basic questions about primes and addition, such as the twin primes conjecture, which proposes that there are infinitely many pairs of primes that differ by only 2, and the Goldbach conjecture, which proposes that every even number is the sum of 2 primes. By an astonishing coincidence, a weaker version of this latter question was settled in a paper posted online by Harold Helfgott of École Normale Supérieure in Paris, while Zhang was delivering his Harvard lecture. Prime numbers are abundant at the beginning of the number line, but they grow much sparser among large numbers. Of the first 10 numbers, for example, 40% are prime, 2, 3, 5, and 7, but among 10-digit numbers, only about 4% are prime. For over a century, mathematicians have understood how the primes taper off on average. Among large numbers, the expected gap between prime numbers is approximately 2.3 times the number of digits. So, for example, among 100-digit numbers, the expected gap between primes is about 230. But that's just on average. Primes are often much closer together than the average predicts, or much farther apart. In particular, twin primes often crop up, pairs such as 3 and 5 or 11 and 13 that differ by only 2. And while such pairs get rarer among large numbers, twin primes never seem to disappear completely. The largest pair discovered so far is 2,996,863,034,895 times 2 to the 1,290,000th plus or minus 1. For hundreds of years, mathematicians have speculated that there are infinitely many twin prime pairs. In 1849, the French mathematician Alphonse de Polignac extended this conjecture to the idea that there should be infinitely many prime pairs for any possible finite gap, not just 2. Since that time, the intrinsic appeal of these conjectures has given them the status of a mathematical holy grail, even though they have no known applications. But, despite many efforts at proving them, mathematicians weren't able to rule out the possibility that the gaps between primes grow and grow, eventually exceeding any particular bound. Now, Zhang has broken through this barrier. His paper shows that there is some number n smaller than 70 million, such that there are infinitely many pairs of primes that differ by n. No matter how far you go into the deserts of the truly gargantuan prime numbers, no matter how sparse the primes become, you will keep finding prime pairs that differ by less than 70 million. The result is astounding, said Daniel Goldstein, a number theorist at San Jose State University. It's one of those problems you weren't sure people would ever be able to solve. A prime sieve. The seeds of Zhang's result lie in a paper from 13 years ago that number theorists refer to as GPY, after its 3 authors, Goldstein, János Pince of the Alfred Renyi Institute of Mathematics in Budapest, and Cem Yildirim of Bozici University in Istanbul. That paper came tantalizingly close, but was ultimately unable to prove that there are infinitely many pairs of primes with some finite gap. Instead, it showed that there will always be pairs of primes much closer together than the average spacing predicts. More precisely, GPY showed that for any fraction you choose, no matter how tiny, there will always be a pair of primes closer together than that fraction of the average gap, if you go out far enough along the number line. But the researchers couldn't prove that the gaps between these prime pairs are always less than some particular finite number. GPY uses a method called sieving to filter out pairs of primes that are closer together than average. Sieves have long been used in the study of prime numbers, starting with the 2,000-year-old sieve of Eratosthenes, a technique for finding prime numbers. To use the sieve of Eratosthenes to find, say, all the primes up to 100, start with the number 2 and cross out any higher number on the list that is divisible by 2. Next, move on to 3 and cross out all the numbers divisible by 3. 4 is already crossed out, so you move on to 5 and cross out all the numbers divisible by 5, and so on. The numbers that survive this crossing out process are the primes. The sieve of Eratosthenes works perfectly to identify primes, but it is too cumbersome and inefficient to be used to answer theoretical questions. Over the past century, number theorists have developed a collection of methods that provide useful approximate answers to such questions. The sieve of Eratosthenes does too good a job, Goldstein said. Modern sieve methods give up on trying to sieve perfectly. GPY developed a sieve that filters out lists of numbers that are plausible candidates for having prime pairs in them. To get from there to actual prime pairs, the researchers combined their sieving tool with a function whose effectiveness is based on a parameter called the level of distribution that measures how quickly the prime numbers start to display certain regularities. The level of distribution is known to be at least 1/2. This is
Sample complete. Ready to continue?